Okay, good evening everyone. Today we'll have a demo session on VLSI design. Okay, so what are the concepts we are going to cover? Introduction to VLSI. What are the different types of ICs? We have the classification of IC, that means generations of IC, and Moore law, or what is it mean by, and improvement in fabrication technology. What are the advanced technology we are using now, and what are the advancements in the electronics from past 19th century, and future of VLSA. What is the future of VLSA? Will VLSA has the future, or VLSA will dead after a nanometer, after it will go to the 1 nanometer technology, beyond 1 nanometer technology? VLSA did have future. And VLSA design flow, that means what are the stages we are using, like what are the design stages involved in the doing the manufacturing of IC. Okay, and what is the difference between ASIC chips, FPGAs, SOCs? We'll see these things, and brief introduction about the simulation and synthesis, and what is meant by Verilog HDL. Okay, these all the things we'll see. If you have any doubts in the middle of the session, you can ask your doubts. Okay, let's recollect the things. Can anyone tell me what is mean by VLSI? Whatever you have the idea, whatever you have the knowledge on VLSI, you can share.
It's a very large scale integration.
Okay.
It all deals about digital electronics.
Okay. What is mean by very large scale integration?
Many of the transistors are
Number of
included in a
transistors are
single chip.
integrated.
Okay. Okay, number of transistors integrated on a single chip, right? Okay. Okay, so introduction to VLSI. Okay, if you see, VLSI is nothing but a integrated circuit. We are integrating number of transistors. Number of transistors in the sense, how many number of transistors? It all depends on the scale. Okay, we have small scale integration, large scale integration, very large scale, ultra large scale. Okay, based on that, how many number of transistors we are integrating in a single chip? Okay, suppose if you see the olden computers in 19th century, okay, this is what the size of computer we have. Okay, a big room size. Okay, in that we have used very old technology. First technology is the vacuum tube technology. Maybe you have seen some vacuum tube computers in your school days. Okay, so those technology we have used that time. 5 MB hardware, 5 MB hard drive. Okay, whatever we are using our hard drives in the computers, in our laptops. Okay, that time we have used in MBs. Now we are using in GBs, right? So that is what we have used the olden days computers, which is very it has very limitations regarding the performance or storage, or like in a speed. Okay, so this is the transformation from olden days computer to present whatever we are using. Okay, in the olden days computer, which is a big room size, to do a single performance, a 2-bit operation, it will take hours of hours. Okay, but nowadays we are using a multiple bit operations, so 64, 124-bit operations we are performing within a seconds, right? So that is the main difference. What that mean? Why this gradual difference? Okay, why? Because in the olden days, whatever the technology we have used, that is not up to date. Okay, that means it doesn't have the features like speed and uh, the size. Okay, wherever we have used the vacuum tube technology, which is a analog format. From the vacuum tube technology we have moved to the diodes. Okay, diode in the sense analog diodes, like a switch, it just used like a switch and to store the data. And then we have moved to the analog transistors like a BJTs. Okay, from the analog transistors we have moved to the FET transistors. Okay, from the FET transistor we have moved to the CMOS technology. Present we are using the CMOS technology. Okay, whenever we are using different technologies, accordingly different type of features has came to advance. Okay, like in the speed or in the performance, in the storage. Okay, in the fabrication wise. Okay, everything we got the advancements. Okay, so that is why we are seeing these small, like a very minimum complexity now. Okay, like a laptop if you see. Okay, that all depends upon our whatever we are using the electronic chip inside the system. Okay, did you got the point, everyone? How we are using those electronic chips, how the transistors are made, everything we'll discuss clearly. Okay. Okay. Yeah, is gallium. Yeah, that is what the olden method. Okay, gallium arsenide is the oldest method. Uh, and present we are using we are not using those type of methods, right? So from the gallium arsenide we move to the transistor family. In the transistor family, first we have used the analog, then FET, then CMOS transistors. Present we are using different fabrication technology, right? Next. So this is how the transformation from the Apple computer, if you see the olden days Apple computer, how it look, even it doesn't have the screen, okay, to display something. Okay, it doesn't have the good screen to display, but present we are using a smartphone, and like Apple phone we are using, which has different features. We can use any technology, we can install all type of apps and all, which supports for everything, multiple purposes. Okay, so that is what the transformation has got. Okay, so what are the classification of integrated circuits? Why we are seeing these much of advancements in the chip? Means, first if you see, before the integrated circuits we have used the transistor. Only by using the transistor the circuits are made. Okay, but from the transistor we came to integrated, that mean number of transistors are integrated in a circuit. Okay, in a chip, in a hardware we can tell. Okay, small scale integration is nothing but only 1 to 10 number of transistors we can integrate in the chip. Okay, then medium scale, if you see in 2000 like that, we have used 1 GB mobile phones, 2 GB mobile phones. Okay, whatever we have used there, those all are medium scale integrated circuits. Okay, just 10 to 500 number of transistors only we have used, and the chip size also very large. Okay, if you see the computers in 2000 computers, if you see, there will be a big processor. Upon the processor we have used the fans also to cool the processor. Okay, so that is the size of processors we have used that time in the large scale and medium scale. But present we are using very large scale, mean the number of transistors we are increasing. Whenever we are using increasing number of transistors, what happens, the size of the transistor is reduced automatically, and then performance is increased. Why? Because whenever number of transistor increases, switching operation is increasing, right? If you see, suppose in small scale integration we have used only 100 number of transistors like this. Okay, but in very large scale integration or large scale integration we have used 20,000 number of transistors here. Okay, present now we are using billion number of transistors. Okay, here transistor size is, suppose if you take in a small scale, here transistor size may be 100 micrometer, in terms of micrometer. Okay, now in larger scale, maybe the transistor size is 100 nanometers or 1000 nanometers. We move to the nanometer, from micrometer to nanometer. Okay, whenever size is reducing, what happens? We can integrate more number of transistors in a same chip, right? So suppose here we are using billion number of transistor, 1 billion number of transistors we are using, which is the size of 10 nanometer in the VLSI. Okay, that means in 100 micrometer transistor, only 50 number of transistor is there. Switching operations are less. Okay, but in 100,000 nanometer transistor, where we are using 1 lakh number of transistors, there are more number of switching operations. Within a seconds, more number of switching operations will be performed. Okay, like mean on off transistor is nothing but it will perform on a on off, right? So like that, when we are using 1 billion number of transistor, that means per second those many number of switching operations are happen in between the transistors. Okay, that means automatically the speed of the transistors are increasing. That means performance is increasing. Whenever size is reducing gradually, automatically we are using very thin thin chips. Okay, did you got the point, everyone?
Yes, ma'am.
Okay, so that is what we are doing here. So that is what the ultra large scale VLSI we are using now. Okay, have any doubts? Have any doubts, everyone? Okay.
Can you tell any practical example?
Practical example in the sense, okay, whatever we are seeing, see, suppose in the olden mobile phones, you know, olden mobile phone in your old childhood, you have used normal like keypad mobile phones, right? Or otherwise you can take the computer, which size, how much size of computer we have used there, like it will be like a big block. Okay, that means if you see CPU in your computer, okay, in CPU there will be a motherboard. What is that motherboard? Inside the motherboard there are different number of components, right? How much size those motherboard components will be there? See, if you understand, suppose we have a CPU there. Inside the CPU, half of the in the motherboard there will be a big processor with a big fan. But are we using that much of processor in our laptops present? Are we using in our laptops present, or in our computers present, or in
More
our
number of
mobile phones?
yes,
In our mobile
yes, ma'am.
phones are we using? No, right? So
Mm.
that is nothing but the difference. Okay, that is the transformation. In 2000, whatever we are using those big processors, in that processors we have used medium scale integration or large scale integration technology. Okay, whereas number of transistors are very less, like in thousands or lakhs. But in 2020, whatever we are using in our laptops, there are very thin processors, and we are not using even fans also. Why we are not using fans additionally means, because internal processor, when they are manufacturing, they are introducing some techniques for like cooling process. Okay, like a hyper threading process. They are introducing those type of techniques internally. Okay, no need to put extra fans and all. Okay, so these are the nothing but how the technology is improving from 2000 to 2020, or if you see 19th century to 20th century now. Did you got my point?
Yes, ma'am. Yes, ma'am.
Okay, have any doubts, others?
No, ma'am.
Okay. Okay, what is mean by Moore law? Can you tell anyone who is Moore?
One of the transistors increased for 4 times per year. 4 years.
Okay.
For every 20 months, the number of transistors will be increased.
Okay.
For every 18 months, transistor will be doubled.
Okay. Good. Good. So who is Moore means he is a co-founder of Intel company. Okay. He given one explanation on integrated circuit. That means in an integrated circuit, the number of transistors will double for every 2 years, approximately 18 months. Okay. Whenever transistors are doubling, the size of the transistor will be reduced to half. Okay. So whatever he predicted that time in 1960s, it is going on still. Okay. Suppose as his prediction in 1960s or in 1960s, we have used we have used 1000 micrometer technology at the time. That means maybe 10,000 number of transistors we have integrated in the chip. Okay. Coming to 1980s, maybe we have used 100 micrometer transistors and number of 1 lakh number of transistors we are integrated on a single chip. And coming to 2000, we have used 10 crore number of transistors in a chip, and maybe 100 nanometer technology we are using or 200 nanometer technology we are using. Okay. In 2022, can you tell me what is the size of transistor we are using in the nanometer technology and how many number of transistors we are integrating on a chip? Can anyone?
8 nanometer,
8 nanometer. Okay.
8, 12, 4.
14 nanometer.
14 nanometer. Okay. 7 nanometer. Okay. 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 7 nanometer we are using and also 5 nanometer we are using. Okay. Present in 2022, we are in a 5 nanometer technology. Okay. And coming to number of transistors means 100 billion number of transistors we are integrating on a single chip. You can estimate the performance, how much speed it is working on, right? 100 billion number of transistors and 5 nanometer transistor means it will be more number of switching operations within a second. Million times it will perform the switching operations. Okay. So that is how the speed we are using in our present mobile phones or in our laptops or computers, whatever. Okay. Wherever we are using the processor. Okay. So this is what Moore predicted already. Okay. The number of transistors in the chip will be double for every 2 years and will be half the size of the chip. The size of the transistor will be half for every 2 years. Okay. Did you got the point, everyone? That's why only we are seeing these many features, like these many advancements in terms of speed, in terms of storage, in terms of very smart, how the devices are working very smart, we know, right? Did you understood, everyone?
Okay, ma'am. Understand.
Okay. Okay, so this is the improvement in the fabrication technology. If you see in earlier days in 2015, like that, we have used CMOS technology, CMOS transistors. Okay, CMOS transistors up to 24 nanometers we have used. Okay. What is the transistor? It has a source, it has a drain, and it has a gate, right? Whenever the size is reducing, can you tell me what is the size, how we can calculate? 24 nanometer size means what? It is the transistor size. It It is the size of the transistor.
It is the width between the source and drain.
Drain,
This
right?
one.
Right, good. So it is the distance between the source and the drain, nothing but a channel width. Okay, channel width we will call as a size of the transistor, right? So whenever the channel width is reducing, what happens? The number of electrons will not flow more number of electrons will not flow. And then suppose here the source and the drain is there, very minimum distance is there. What happens here? Will get lot of limitations, right? What are the limitations we'll get? What are the limitations we'll get when the size of the transistor is reducing? That means distance between source and the drain is reducing. Maybe short circuit effects will get, right? And also the electron whatever moving from source to drain, it may penetrate into the gate. Sometimes it tunnel into the gate, right? So tunneling limitations can be get short circuit effects, and current leakage effects also will get, right? So when we are using the CMOS technology by the 24 nanometer, we have seen these type of limitations like a current leakage and gate tunneling. Okay, so that's why from the CMOS technology we have moved to the FinFET technology, which is the advanced technology in the fabrication in the transistor. Okay, nothing difference is there. In the planar we have used in the like this horizontally, but in FinFET we have used this body as a vertically. Okay, these type of structure changes we have made. Okay, by using these structure made changes, we can reduce the limitations like a short circuit effects and channel current leakage effects. We can reduce these limitations. Okay, that's why we have moved to the FinFET technology. FinFET technology also up to 10 nanometer only. Again, when it reaches to 10 nanometer technology, when the distance between source and the drain has reduced, so again it also got the limitations, same limitations. That's why we have moved to the GAFET technology, gate all around. Okay, that means this gate has divided into a nano wires like this. Okay, by using this technology, at 5 nanometers and 7 nanometers, we can we can able to send the signal, like we can avoid some current leakages and short circuit effects. Okay, so GAFET technology, and after some time when it reached to 5 nanometer, we got the limitations in GAFET also. Then we are using the MBC FET nano sheet. Okay, here we are using the nano sheet. That is how we are transmitting the current from the source and the source to drain. Okay, did you understood now? So this is how the fabrication technologies are improving day by day. Okay, have any doubts?
No, ma'am.
Okay, here my question is, suppose here MBC FET we are using at a 3 nanometer, suppose if we think. Okay, suppose if transistor reduces to 1 nanometer, what happens? If transistor reduces 1 nanometer means very minimum distance between the source and the drain, right? So what happens at that time? 1 nanometer or beyond 1 nanometer?
Short circuit may occur.
Okay, short circuit may occur. Okay. Any other?
Ma'am, could you please repeat that point, what you had said for MBC FET?
MBC FET, I also don't know what is the full form. My question is, Suppose in MBC
Not
FET we are
silicon.
yeah, in MBC FET we have used nano sheets technology. What I am telling is nano sheet. Here wires in the sense wire means maybe the width is more compared to the sheet. Nano wire width will be the more the size. Nano wire to nano sheet we are reduced very. Suppose here nano wire means 5 nanometer. Nano sheet is 3 nanometer. Okay, so that is how we reduce the size. My question is,
But
if tell.
Ma'am, it will approach to atomic radius, I think.
Okay, okay.
if we are using these project of reducing the size, it will also affect the source to drain distance, no ma'am.
Mm, yeah, that's what I am telling. Here 3 nanometers. After 3 nanometer also, here it will affect the source to drain. We need to move to 2 nanometer, 1 nanometer like that. Right? Once transistor reaches to 1 nanometer or beyond 1 nanometer, what it happen? Will transistor work? Will it perform the switching operation? That's what I am asking.
No, ma'am.
Okay, no. Then what is the advanced technology? Will VLSI dead after 20 years and next coming years? If transistor reduces to 1 nanometer or beyond 1 nanometer, we cannot perform the switching operation. Transistor will not perform its original operation. Okay, it loses its functionality. Okay, so at that time what can we do? Without a transistor, will VLSI dead? Without a transistor means there will be no integrated circuit, right? In that time VLSI will dead or what? Is there any advanced technology? No idea.
No idea, ma'am.
Okay, SOC, all these are SOCs only. SOC means what? A system on chip. Previously, we have used motherboards. Present in the mobiles, we are using system on chips. In the system on chips only, we will have the processors, right? In system on chip, what we'll have? This is a SOC. We'll have processor cores, number of cores. Suppose you are using 8 number of cores, 4 number of cores. There will be memory units, graphic processor units, and there will be some ports like C port, USB ports, and there will be camera modules. Internally, there will be so many subsystems will be there. Okay, in the SOC only here there is a processor. In this processor only we are using cores. In the cores we are using these transistor technology and all, right? Of course all these also we are using hardware only. All these we will use the transistors and all. That's different thing. Did you got everyone? No idea? Okay, so if you see what the advancements in the electronics. As we discussed, at starting we have used the transistor technology, then we move to integrated circuits, then processor. Processor is nothing but all these integrated circuits are connected within the single processor. Then these are the analog processors. From analog processors to we have moved to the digital signal processor. Okay, you have the DSP subject also. Digital signal processor is also a huge topic. Okay, and then FPGA and a ASIC. What is the difference between FPGA and ASIC? Can anyone? What is the difference between FPGA and ASIC?
FPGA performs a specific task, ma'am, but when compared to ASIC, it can perform multiple tasks.
No, purely opposite. ASIC perform multiple tasks. You said that only?
Yes, ma'am.
No. Anyone?
ASICs are used for only specific task.
Okay. Can you tell any examples for FPGA and ASIC? FPGA is a field programmable gate array. ASIC is
Mobile
the
US.
ASIC is the application specific integrated circuit. In the name it had, right? Application specific integrated circuit. Only specific applications we can use the ASICs. Okay. ASICs are nothing but whatever the processor we are seeing. Okay, all those are ASIC chips. Whatever the chips we are using in our mobile phones, in our laptops, like that. Okay, it will perform only specific operation. Whereas FPGA, can anyone tell examples for FPGA?
Spartan, like one name is there, Spartan from
Okay.
Giants.
Yeah, those are the series in the FPGA. Okay, but FPGA in the sense it will perform the multiple task, whatever the requirement. Suppose I want to perform a traffic light controller using the FPGA. It want to work like a traffic light controller, or it should work like a digital watch. It should work like a digital alarm. Like that, I can code the design and I can dump into the FPGA. That's how FPGA will work with a different task. Okay, it is a reprogrammable. Once if you do a specific a functionality or a project, again you can use that FPGA for another project. It is a reprogrammable. Whereas ASIC chips are the permanent chips. Whatever we are using our chips, processors, those are permanent. Once the manufacturing unit, once the hardware dumped into the design with the software, it doesn't change again and again. Once it damage also, we need to just throw into the dustbins. It doesn't change. We cannot reprogram the ASIC chips. Those are the permanent chips and will perform the specific operation. Did you got the point idea, everyone? Is
Yes, ma'am.
FPGA used in drone? um Not in drone. uh, how the drone will fly, like will have a code, will connect the drone to specific Arduino, right? That right. So those type of Arduinos are nothing but FPGAs only. We'll call it like a FPGA only, because those are the reprogrammable. Okay, drone means we can reprogram it. If you want to fly right side or left side or somewhere, like we can reprogram it whatever the application needed. Okay, did you understand? Okay, have you understood the difference between FPGA and ASIC? We'll see how ASICs are designed and how the manufacturing process, everything we'll see now. And after that, SOC. SOC, I discussed so many times how SOC look like, and what are the subsystems will have, and what is meant by IP level, SOC level, subsystem level. I think we discussed all these things so many times. So that is what SOC, system on chip. That means all the blocks will be integrated on a single chip. Okay. Did you have any doubts up to here? Anyone?
Ma'am, difference between ASIC and FPGA means FPGA can be reused in another projects. Like we can enhance the advancements.
Yeah, yes. FPGAs used for reuse for different times, so like a student level, or suppose a processor is going to design. Okay, a processor is coming to the market. Okay, if we want to check whether the processor is working correctly or not, all the functionalities are working correctly or not, we cannot manufacture directly. It is a waste of cost. If we got any errors like that, what it just waste of cost, waste of material, right? So at that time, sir, we can use the FPGA. By using the FPGA, the design engineers or manufacturing unit will check the entire design is working correctly or not, functionality is working correctly or not. Then they will move the design to the permanent chip, ASIC chips. Okay, like FPGA is a reprogrammable and doesn't waste the it, it doesn't waste the um like physical chip. Okay, did you got the point now?
Yes, ma'am.
Okay, okay. Have any doubts? Others? Okay. Now my question is, what is the technology we can use if the transistor moves to 1 nanometer technology? Will transistor dead or what happens? Can anyone? Okay. As
We'll
we
move to
discussed,
FPGA technology, ma'am.
FPGA technology is a older technology. See, from the FPGAs, from the ASICs, we came to SoCs, system on chips. Okay, FPGA. See, FPGA is a block. Okay, wait, I will show. Suppose this is what FPGA. Okay, in place of system on chip, if you want to use FPGA, what you will do? You need to use one FPGA as for memory, one FPGA as a camera, one FPGA as a graphic processor, one FPGA as a processor, and one FP. These many FPGAs you need to use in a circuit. Okay, but FPGA, you know how much big size it will look. Okay, it is very big size. That mean in the sense like arduinos, if you see any arduino in IoT devices, that like same it will be look like arduinos and all, if you see here. Okay, so you cannot use FPGAs for designing the chips. FPGA is the oldest method. Even FPGA we won't use practically. Okay, ASICs are used practically for mobile phones or laptops or computers. That also older version. Present we are using SoC. That means all these things are can be integrated on a single chip, this much of chip, small chip. Okay.
No, ma'am.
Yes, ma'am. Got it.
Okay. Okay, so what is the future of VLSI? As I told that if transistor size is reduced to 1 nanometer or beyond 1 nanometer, what is the future of VLSI? Will VLSI dead? Means no. Okay, here comes the picture of quantum technology. What is mean by quantum technology? Have any idea? Anyone? What is mean by quantum technology? Maybe when you are studying intermediate or first year BTech, you have listened like quantum theory, quantum mechanics, and atom, neutrons, protons, right? Electrons. That means the electrons will be rotated around the atom by rotating itself, right? So that quantum mechanism, that quantum theory we will use here. Why? Because whenever transistor is reducing to 1 nanometer technology, it will penetrate the electron may be penetrate or tunnel into the gate. There will be a short circuit effect. Okay, we cannot predict how many electrons will be there, because very minimum size, maybe very less number of electrons will be there. Okay, by using those many electrons, the less number of electrons, we are using the quantum theory here in a atomic level. Okay, in a atomic level, the quantum theory have the some concepts like a superposition, entanglement. By using the electron have the property of a superposition, like that. Okay, that is another topic. When we have the time, one day we'll discuss about the quantum technology, everything. Okay, so by using the quantum technology, we are going to design the circuit. Okay, those things we'll discuss the quantum technology again. Okay, now my question is future of VLSI. What is the future of VLSI next coming 20 years? Implementation of AI and machine learning in the VLSI design technology. Is it possible to implement artificial intelligence and machine learning in VLSI design technology? Can anyone? Whatever you have some idea, you can explore. Okay. Maybe you do you have idea on machine learning and artificial intelligence? Machine learning is a subfield of artificial intelligence, right? Which is a capable of it is a like intelligent human behavior, right? Artificial intelligence system are used to perform the complex task in a way to similar how humans are solving the problems. Okay. Simply, if we say machine learning denotes the artificial intelligence system as a self learning based on the algorithms. Okay, algorithms are nothing but whatever human design based on the algorithms, artificial intelligence is going to work, right? So, whenever system getting smart over a period time without the human involvement, okay, that defines the machine learning and the deep learning, whereas a machine learning is applied to the large data sets. Okay, that means it will involve more layers of data analysis, right? So artificial intelligence involves the learning because it has a smart behavior that requires the uh, that requires information to observe to the new methods, right? So, how the new techniques in machine learning are being implemented? How we are implementing new techniques? Can anyone? As we are using the hardware systems, how we can implement the new hardware systems using the machine learning to get high performance? Suppose if your evolving time is increasing, okay, machine learning will require improved custom hardware, right? Whatever we get the technology like a AI or machine learning or deep learning, every technology should have a hardware, right? So machine learning will require the hardware to meet the design developments. Whatever their developments are there, it should have a hardware to require their developing things to improve their customized things. Right? Hello. So if you look here, the domain and the scope of the machine learning is very fast. Okay, in upcoming days, whatever we are using the automation mobiles or automation gadgets, whatever, this works under machine learning and artificial intelligence, right? So many investors and developers are already in the market working toward the upgradation in the VLSI. Okay, the systems and technologies are based on algorithms, model trainings, rules, etc. If you see, we will have some algorithms and model trainings in the machine learning as well as deep learning, right? So, however, there is a need to understand that the software requires very high end hardware as the significant computation capacity, right? To to explore that capacity, to meet those to meet those computations, we should have a hardware, right? So which consumes the less power and which is capable of performing the complex mathematical functions and which performs in a just a seconds, within a fraction of seconds, right? We should have that type of hardware. Okay, so here the electronics behind, did you understood? So here the main picture of electronics. Okay, so the advancements in the chip technology, graphical processing units or sensors or communication networks, etc., have come to rescue and development of AI. Did you understood point? So electronics and communication engineer will play a very important part in this. In future, artificial intelligence techniques in VLSI domain, in VLSI automation, tackle the various issues of multiple design stages. Really, the VLSI design automation tackle the various issues, various multiple design stages. Okay, example, it is a well-known fact that the machine learning models cannot be trained on the computer processing units due to their inefficiency. Why inefficiency? Because it doesn't have the high quality data sets. Okay, mostly it is not preferred for images and videos. Okay, here VLSI comes into the picture. VLSI engineers designs a graphic processing unit to overcome the problem. Okay, so similarly, all kinds of hardware that artificial intelligence requires can only be fabricated by the VLSI industry. It can be started by the VLSI domain, and artificial intelligence are co-dependent. Okay, here the VLSI domain and artificial intelligence are co-dependent. Did you understood my point, everyone?
Yes, ma'am.
Did you got everything, everyone? So in future, VLSI domain and artificial intelligence are codependent, because whatever the advancements we are getting, whatever it is, okay, maybe in statistics, whatever it is, they should require a hardware. Okay, so that is the fact behind it. And so if you consider any applications such as a washing machine or cell phones or micro ovens or ACs, any electronic devices, okay, and anywhere, everywhere, like a defense, okay, if you see in a defense, okay, everywhere electronics has penetrated. Okay, the digitization race is going every day for new electronics. Can you please mute? Okay, so we should have a low power consumption, high battery backup, low cost, fastest computational speed, and very short design time. Very short design time is also very important. Okay, if you design a processor with years and years, what is the use? No use, right? So that is also very important. Okay, so compare it to the olden methods, whatever the coming methods are there which are exclusively strategies of artificial intelligence. Okay, there are several methods for handling complex and data concentrated tasks in the testing for VLSA. Okay, there will be so many advanced methods out there. Okay, so these complications and these things will be overcome by the embedded or incorporating the latest technologies in the design VLSA and the manufacturing. For this purpose, they will involve the new technologies in the VLSA. That is one thing quantum technology we can call. Okay, did you got the point, everyone? So, like artificial intelligence and machine learning is to understand one of the concept of deep learning. Okay, if you have the idea, deep learning is a subsection of machine learning, right, which has a simple terms of neural network in the with the more layers. It has the layers. Okay, if you see whatever our human brain has there, like a neural network like this, deep learning also designed with these neural networks, if you see. Okay, based on these neural networks only, future future of AI or future of VLSI is going to happen. Okay, did you got the point, everyone? So VLSI not dead. Coming the new version. Okay, it is going to step into the new version of VLSI, which is a collaborate with the AI. Did you understood, everyone?
Yes, ma'am.
Okay. So what is mean by quantum technology? As I discussed, when the size of the transistor is reducing to nanometer, obviously we are using the quantum theory, quantum mechanics here. Okay, so quantum technology that works by using the principles of quantum mechanics, and it includes the entanglement and superposition principle. Superposition principle is the electronic for electron. Okay, based on like if you see like a spin property. Suppose electron has a spin property based on spin up and spin down. It is going to store the data. Okay, by applying the magnetic artificial magnetic field, we will stabilize the electron here and it will store the data. That is another concept, that is also a huge concept. We can discuss later on. uh, Another class I will take for quantum thing, quantum technology, will discuss those things. Okay, so in the quantum technology, in the quantum computing, instead of using the traditional bits, whatever we are using a 0 1 bit like that in the classical computers, whatever we are using, in the quantum here we will use the qubits. Okay, qubits means that have a properties like quantum tunneling, superposition, and quantum coupling for the data transmitting. Okay, so this is how we are using the future technology. It is very, very, very fast technology. The data can be transmitted 100 gigabits per second. That much of fast technology we are using in the coming days. Okay, did you got the point, everyone? Have any doubts here? Have any doubts about the difference between ASIC and FPGA? We have discussed already. FPGA is a ready-made chip. Okay, we can use for any like a reprogrammable for your industry level projects or student level projects. Okay, it will perform like it doesn't have high speed, just it will perform like a project level. Okay, and whereas ASICs or the we need to dump the original design into the ASIC. It is a permanent chip. Okay, it works under high frequencies. Okay, and the energy is efficient, and whatever the power it consumes, the less power compared to the FPGA, whereas FPGA consumes more power. Okay, so that is the main difference. And FPGAs are limited with the bandwidth and operating frequency. Okay, have any doubts up to here? Okay, whatever we are seeing ASIC chips or SoC chips, okay, we will follow the design rules. Okay, manufacturing process. Okay, what is the process of manufacturing? What are the different levels we have? What how we'll follow? Okay, first we'll consider the specification. What is meant by specification? Okay, every company have different specifications. Okay, suppose whatever the processors they are manufacturing before. Okay, suppose before they have manufactured some X processor. From that X processor, what is the market is expecting more? What are the advanced features market is expecting? Okay, and how can we bring up the new features? And what are the advancements we can take? And what how power consumption we can reduce? And what how the speed can be improved? And what is the fabrication technology we can improve? How can we improve? All these things will be taken from the market requirement and old processor, whatever their old project is there. From the old project they will take the specifications and they will add the features. If there are any features to be removed which are not used or which are not which are not improved in the market, which are not highlighted like that. Okay, they remove those features and they will add the new features according to the feature specification. They will send the suppose this is what they designed the architecture manually in the specification. Okay, so in the architecture there will be several blocks will be there. They will assign, there will be lot of teams will be there, number of teams will be there. In every team there will be a senior engineers and there will be a junior engineers, trainees like that. And each team will be collaborate with the other team. Okay, suppose that this is a processor core team and this is suppose there will be a DFT team, physical design team, or any some whatever the memory team will be there and the processor team, like that, whatever the blocks will be divided into the each team, and according to the specification the team will be design the circuit. Okay, once each design team completes their specific task, the whole circuit will be sent to the verification engineer. Okay, so the verification engineer will work accordingly according to the design features. They will consider the design specification. Based on the specification, they will check, they will do the verification by using the system verilog and UVM. Designing is done by verilog HDL. System verilog and UVM is for verification. Okay, so they will generate the test plans according to the specification. Each team will generate the specific test plans and specific test scenarios. How we can meet this scenario, how we'll meet this feature, by using which scenarios we can meet this feature, like that they will check. Okay, so according to that they will develop the test plans, test features and all, and they will work accordingly. They will work no, verification. Okay, once verification has done to overall ip level, they do the verification. Each ips will be divided to the each team. Every ip team will do the verification on each ip. Okay, once ip level verification has done, they will do the subsystem level. Once subsystem level has done, they will move to the soc level, like that. Okay, in soc level we will use the C++ language, because there will be a course will be connected to every IP. Suppose here there is some memory IP, or we need not to tell exactly. So I'm just telling as a memory or graphics, like that. Okay, so every core we have to connect with the every IP. So that means every IP will be connected to the core, which is a here we will use the C++. Why? Because core means these all microprocessor. I think you have learned the microprocessor language in your school days. Sorry, in your BTech level. Microprocessor language, move hexadecimal something value, move like those many instructions we will use, right? Fetching, decoding, moving to the opcode, operands, like that, that language we will use for core. Okay, so that's why here system verilog or uvm language it doesn't understand. Okay, C language is comfortable for the core. Okay, that's why we will use the C language for soc level. Okay, so all this verification has done, then will this circuit will move to the, this design will move to the physical design. Physical design means all back end process. Okay, back end process, it will check for physical design verification and sign off, layout, fabrication, testing, it will check for floor planning. First it will take the silicon wafers, floor planning, then it will do the partitioning, floor planning, placement, clock tree synthesis, signal routing time. There will be so many things in the physical design also, like a DFT team, validation team, testing team. So many teams will be involved in the physical design, as well as in verification also. So many teams involvement will be there. Okay, so this is how we'll do the overall verification, design and verification. Did you understood everyone? Did you understood everyone?
Okay,
Have
ma'am.
any
Understood.
doubts? Okay, so this is not as simply as we seen here. Okay, we just seen only 10 number of blocks only, but internally there will be so many thousands of teams will be there in SOC level verification. Have any doubts, everyone? If you don't have
No,
doubts, we
madam.
can close the session. Okay, so that is what the verification, designing and verification will happen. And next, tomorrow there will be a demo session on system verilog. System verilog and UVM batch is going to start from tomorrow. Tomorrow there will be a demo session on SP and UVM. So if you are interested, you can join. Okay. Then thank you.
Thank you.